Alright, in this lesson we are going to discuss factoring the special cases. These are a couple of special types of factoring that we will learn. So let's continue. So let me start by looking at this multiplication problem. If you were going to multiply x plus 5 quantity squared, you would need to multiply 2x plus 5's. Of course, this is a FOIL situation, and we're going to end up with x squared plus 10x plus 25. Now we call this this answer here a perfect square trinomial. First of all, it's a trinomial because it has 3 terms, but then notice what we have here is equal to x plus 5 squared. So this trinomial is equal to something squared. That's what makes it a perfect square trinomial. So when we have perfect square trinomials, it turns out these are pretty easy to factor. So if we were starting with the x squared plus 10x plus 25 and we had to factor this, we could certainly use the AC method. But when I see these perfect squares on the ends, then I would try what's called trial and error. Notice if you look at the x squared, let's see here. I guess one thing we want to make sure we know how to do is recognize our perfect squares. So you should know at least up to 12 squared, which is 144. For example, another one would be 11 squared, which is 121. So you really ought to know these. So if you were factoring this trinomial, you would first look at the x squared and notice that if you go back to the binomials that multiply to give us this trinomial, it's x times x that gives you the x squared. Then we look at the 25, and 5 times 5 is 25. And so if you actually FOIL this out, you can see that these are equal. So let's go ahead and do a few problems, and we'll use the pattern that we're seeing here. So when I see the x squared and the 36 here, I can see that this is probably a perfect square trinomial. So first we're going to ask ourselves, what is equal to x squared? Well, that's x times x, and then what times itself is equal to 36? That would be 6 and 6. Now, it's either 6 times 6 or negative 6 times negative 6 in order to get 36, positive 36. Since our middle term is negative, they must both be negative. Now we want to make sure that the minus 12x is correct. If we look at the inner and outer product, we get a negative 6x and another negative 6x, which does give you minus 12x, and so that is correct. And so our final answer we would write as x minus 6 quantity squared. Let's go ahead and do another example. So again, if you look at this, it looks like it's a perfect square trinomial if you just look at the ends. So first of all, we'll look at the x squared. We know x times x gives us that. 49, we know that's 7 times 7. Everything's positive here. So again, we want to just double check that our inner and outer product add up to 14x. And notice 7x and 7x does give you 14x. You could also FOIL x plus 7 times x plus 7. That would be another way to check it, but we've kind of already done part of the foiling process, so we really just need to check the inner and outer product and make sure we're getting 14x here. So our final answer, again, x plus 7 quantity squared. Alright, so again, it looks like we have a perfect square trinomial. Notice the 4x squared, you could think of that as 2x times itself, or 2x squared. So certainly the 9 is a perfect square. So we know 2x times 2x gives us the 4x squared. 3 times 3 gives us 9. And it looks like both of our signs are going to have to be negative here, because a negative times a negative 3 would give us, a negative 3 times negative 3 would give us the positive 9. and then we have a middle term that's negative, so these would have to both be negative. Again, we want to double check that our inner and outer product add up to negative 12x, and they do. And so our final answer is the quantity 2x minus 3 squared. Again, I want to remind you that this problem could be solved using the AC method, but if you notice that it looks like, if you notice those perfect squares on the ends, this would be my first guess. If it didn't work, then I would go back to the AC method. Alright, let's look at another one. Notice the numbers are getting bigger. This one's not so nice. If you were using the AC method, I would not want to multiply 16 times 25. It's a pretty big number. So those are perfect squares on the ends. So we know 4x times 4x is 16x squared. 5 times 5 is 25. Everything's positive. So again, we just want to check that our inner and outer product is equal to 40x, and it is. And so we have a final answer of 4x plus 5 quantity squared. Let's do another example. This one, again, if you look on the ends, we do have perfect squares. We do have another variable involved, that would be the y, but it works very much like what we've been doing. We do have our perfect square, so we know x times x is x, or x squared. 8y times 8y is 64y squared. Both of our signs are going to be negative. Again, we want to check our inner and outer product and make sure we get negative 16xy, and they do. And so our final answer is x minus 8y quantity squared. Let's look at the next one here. Now notice this is not a perfect square trinomial. 2x squared is not a perfect square. There's nothing times itself that gives you 2x squared. The 2 is the problem, and the same thing with the 18. However, think about how when we factor, if there's a common factor, or greatest common factor, we need to factor that out first. And so we need to factor out a 2 first. And so we're going to get 2, let's see, 2 times x squared is the 2x squared. We need a minus 6x to get the middle term of minus 12x. And 2 times 9 is 18. So notice what's inside the parentheses. Now that looks to be a perfect square trinomial. So we know x times x is the x squared. 3 times 3 is 9. Our signs are going to be negative. Again, we can check our inner. Let's go ahead and put the 2 in there. We can check our inner and outer product, and those should add up to negative 6x, and they do. And so this is our final answer, which we can write as 2 times the quantity x minus 3 squared. Alright, let's move on to the other type of problem in this section, another one of our special cases. So if you were multiplying x minus 4 times x plus 4 using FOIL, which we've done before, notice we have the same exact terms, x and 4. The only difference between the two binomials is one has a minus and one has a plus. Anytime you have this pattern, something special happens. So if I FOIL this out, notice that my inner and outer product are going to be 4x and a minus 4x, which add up to 0, so we're left with the two terms, x squared minus 16. And notice both of those are perfect squares. So, and this is subtraction, so for that reason we call this a difference of squares. I think it's important that you can identify these because we factor these differently than we do the other things that we've learned how to factor. Alright, so let's do a couple of examples. We've got x squared minus 25, certainly a difference of squares. So we know we're going to have two binomials, and we need to find something times itself that's x squared, and of course that's x. Something times itself that's 25, and that would be 5. 1 minus and 1 plus. Let's move on to the next one. Here we have another difference of squares. 144 is 12 squared. So it's going to be x times x gives us the x squared. 12 times 12 gives us the 144. 1's minus and 1's plus. Remember again, when you factor a difference of squares, you're going to get the exact same terms, x and 12 in this case, and the signs will be opposite. Number 3. Again, we have a difference of squares here. Something times itself equal to 4x squared, that would be 2x. And we need something times itself that gives us 25y squared. That would be 5y. 1 minus and 1 plus. Let's move on. Number 4. Now notice this is not a difference of squares. Certainly 3 is not a perfect square, and neither is 27. But remember, if there's something that our terms have in common, we need to factor out the GCF. So here we can factor out a 3. Now if you look inside the parentheses, what we have there is a difference of squares. So let's factor that. And then don't forget to have the 3 in the front. So your answer here is actually going to have 3 factors. 3 times x minus 3 times x plus 3. Let's do one last problem. So look at the x to the 4th. X to the 4th is a perfect square. In fact, it would be x squared squared, or x squared times itself. So instead of having x and x here, we're going to have x squared times x squared. And then 4 times 4 is the 16, 1 minus and 1 plus. Now, if you notice what our answer here, we have another difference of squares that we can factor. The x minus 4 can be factored, x squared minus 4 can be factored as x minus 2 times x plus 2. Turns out we cannot do anything with a sum of squares, and so this is our final answer. So let's talk about that situation with a sum of squares. Can we factor a sum of squares? Well, if you were to take a guess, at least what most people would guess, is that x plus 2 times x plus 2 would be our answer here. But if you actually FOIL that out, we're going to get x squared plus 4x plus 4. So we have an extra term, the 4x. So in fact, we cannot factor a sum of squares, at least not using real numbers. So at this point, that's the best we can do. We just can't factor it. So the answer here is no. And that's it for this lesson.